many C4 free graphs on n vertices are there? You might want to ask, how many triangle free graphs with a given number of edges are there? You might want to ask, what is the extremal number in GMP of a triangle? You might want to ask, does GNP arrow a triangle? So what do these things mean? This is just the number of edges in the largest triangle-free subgraph of GMP. So we already discussed this, I think, at least at some point. So this is the maximum number of edges in a graph that is triangle-free and is contained in GMP. This is a random variable, right? It depends on GMP. This means the arrow notation is from Ramsey theory. So this says, suppose you take GMP and you two-color the edges, red and blue, do you necessarily get a monochromatic triangle? So is it true that for all coloring of the edges of GMP with two colors, there exists a monochromatic triangle? Okay, so these are four problems that all look somewhat different from each other. Good. Perhaps I'll add another one. So problem if S is a subset of 1 up to n, it's p random. So you choose each element independently at random probability p. Is it true that Roth's theorem holds in S? Is it true that for all A subset of S, size of A is at least delta times S, there exists a 3-term AP in A? So all these things should be, this should be with high probability, this should be with high probability, this should be with high probability, right? And these are counting results. Okay, so how would you go about trying to answer any of these questions? Let's maybe take this one. This is perhaps the no, perhaps actually, let's first, for all 5, let's guess the answer. Okay? So without proving anything, let's just try and guess what we think the answer should be. So how many C4 free graphs are there, do you think? Let me give them numbers. So 1, 2. So I'm not going to solve all these problems today. But I'm going to tell you about a general method that can be used to solve all of them. Let's sort of see roughly what's going on. So how many C4 free graphs do you think there are? Yeah, exactly. There's at least 2 to the end of 3 over 2, because you can take any subgraph of an extremal graph, and I told you that there existed these extremal graphs that look like projective planes. Right? This is subgraph of a projective plane. And it's a theorem of Kleitman and Winston from 82. There's at most 2 to the big O, n to the 3 over 2. Yeah, so it's true up to a constant factor in the exponent. This paper, by the way, sort of should be things like the starting point of the thing I'm talking about today. They introduced the method which eventually became this general method. It's not just for historical curiosity. It's not known what the correct constant is. In particular, it's not known if it's 1 particular 1 times the extremal number of C4. It's a well-known and seemingly difficult open problem. Okay. 2. How many triangle-free graphs with m edges are there? Give me a construction. Yeah, right. There's at least n squared over 4, choose m. Right, take a complete bipartite graph, take any m edges. And this is, maybe it's Wuchak first proved this, I think. This is roughly correct if m is much bigger than n to the 3 over 2. What about if m is smaller than? Go ahead.
Wouldn't we just take the lower bound should be 2 to the n squared over 4?
No. Why?
You're fixing m edges.
Yeah, exactly. I'm fixing the number of edges. If you take a random subgraph, or an arbitrary subgraph of this guy, you'll have some other number of edges.
Okay.
Like I really want to have this number of edges.
Okay.
Yeah. Right. So if m, it turns out m is reasonably large, then this is really the best thing you can do. And actually something stronger is true. Oster's problem and Taras proved that if m is a bit bigger than this, like by root log n or something, then really almost all triangle-free graphs with m edges are bipartite. So it's really strong in a very strong sense. But what happens if m is smaller than this? Well, it turns out that if m is smaller than this, the structure disappears completely. And actually, most of them are completely random-like. So if So the graph looks bipartite if you're bigger than this. It looks random-like if you're smaller. So it turns out the best thing to do is really just take a random graph and then kill the triangles. That gives you a huge number of graphs with the right number of edges, and it turns out it beats this when m is smaller. So we'll see this again in a second. So what about number 3? So perhaps this sort of transition also occurs here, and it's a bit easy to see. So let's discuss it with number 3. What do you think the extremal number of K3 is? Extremal number in GMP of the triangle. I think we already talked about this. So give me a construction. I mean, the constructions are always the same, so you're not supposed to think of anything too crazy. Yeah, by Pareto, right? So you're at least p times n squared over 4, roughly, everything up to 1 plus little o1. So perhaps I should say a half plus little o1 p n choose 2. Always.
With high probability.
Yeah, with high probability. Everything with high probability. Can you do better sometimes? Who can beat this construction, at least for some values of p? When p is big, when p is small, something. Right, so yeah, so you can really get sort of essentially everything. Certainly if p is much smaller than 1 over n, because actually you get to keep all the edges then. But you can do better than this if you just want asymptotically. So if p is smaller than this, the number of triangles, p cubed n cubed, is much smaller than 1. But if the number of triangles is bigger than that, but still smaller than the number of edges, you can destroy all the triangles without removing many edges. Right? This thing is if p is much smaller than 1 over root n. Right? So you can go all the way up to 1 over root n. You can keep almost everything. And then above 1 over root n, okay, this doesn't work, but this still works. And it turns out these are actually correct. I mean, this one's clearly correct. Can't do better. So this is also correct for all p bigger than 1 over root n. This is proved by, maybe I'll give it to Frankel and Rödel. So Frankel and Rödel in the 80s, 86 something, proved some very slightly weaker version of this. And it was maybe tightened up by Korikawa, Wuchak, and Rödel in the 90s, and then generalized. Okay. Yeah, so what's happening? What's happening at this transition? This is happening. The number of triangles reaches the number of edges. So when the number of triangles is smaller than the number of edges in a random graph, then the triangles, they don't really interact very much, right? They don't share edges typically. So they kind of you can deal with them separately. But once the number of triangles is larger than the number of edges, suddenly each edge is in lots of triangles. The triangles are interacting like crazy. And what these results are saying is, above this point, once the triangle is interacting, you have to do something global. You can't deal with them one by one. You have to cut out everything, just take a bipartite graph. That's the best thing you can do. Okay, so this interaction between the triangles is forcing you to do something completely different. And a typical triangle-free graph goes from being unstructured to structured, and the extremal result changes by a factor of 2. Something at the same point for the same reason, same heuristic reason.
Could you explain again the first lower bound for p greater than 1 over square root?
So this lower bound holds essentially always. You just intersect GMP with a bipartite graph. So you just take some bipartition and just take the edges of GMP that are here. And there's basically this many of them.
You are saying that the probability that there is an edge inside is very small.
No. I'm saying we're intersecting GMP with this graph. We're only taking the edges of GMP that lie between these classes. We're throwing away the ones inside.
Okay.
This is a subgraph of GMP. Yeah. So perhaps you can guess the answer to question 4 now. So, probability GMP arrows K3 tends to 1, 0 if P, small, big. Right, there's an increasing property in P. The more edges you have, the best chance you have of a triangle. So there should be some threshold. What do you guess the threshold is? 1/√10. The same thing, right? So in this case, the zero statement, this is harder to see. It's not easy to see that just because the triangles don't interact much, then you can color without creating a monochromatic triangle. But it turns out you can. I mean, it's very sparse, as you can see. Just each triangle, make sure it's not monochromatic. You know, triangle by triangle, making sure that two edges get different colors, and hope you don't get stuck. And if they don't interact too much, then you don't get stuck. Once they do, then you do. Right? And this result says that actually, you really can't avoid this. But this is also not easy to prove. This is also Frankel invariable. This is also this was their motivation for studying this object. And 5. This is perhaps a bit less obvious. So it's not completely obvious here. And maybe as I've written it, it is increasing. So the probability that S is, okay, S has this property for all A in S, size of A is at least delta times S, exists a 3-term arithmetic progression in A. Probability of this event, so the probability that Roth's theorem holds inside S, right? Is it clear what I mean? Tends to 1 or 0 if P is bigger than something, P is smaller than something. Any guesses? Yeah, 1/√10. But why this time? Why is 1/√10 the natural guess? So one reason is because it was the guess here. But there's a better explanation. So that's perhaps an intermediately good reason. So an even better reason is, what's the expected number of 3-term arithmetic progressions in S? S is a random subset of 1 to n. How many 3-term arithmetic progressions are there in n? Roughly. Yeah, you're already correct. N squared, right? You pick the starting point, and you pick the common difference, and that determines it, right? So there's roughly n squared of them. Each one is present in S probability p cubed. And when is p cubed roughly equal to the size of S? What's the size of S? It'll be p times n. Right? So this occurs when p is 1/√10. So it's when your number of 3-term arithmetic progressions is roughly equal to your number of elements. So your 3-term arithmetic progressions start interacting. Okay, so it's happening for the same reason. And maybe it's a slight coincidence, though, okay, perhaps we'll see that it's not such a coincidence. So this is the number of 3-term APs. This is the number of vertices, number of points. And so when these two numbers are equal, that's the point at which the 3-term APs start interacting. Vertices start sharing 3-term APs. So it's the point at which you stop being able to do something local and you have to do something global, basically. Okay, so there's these things all, they look sort of similar-ish to each other. So perhaps it's a hint there should be some kind of general way of attacking them. So let's think about this one. So how might you go about proving? So theorem, the extremal number GNPK3 is at most a half plus delta p n choose 2 if p is much bigger than 1 over root n. Okay, so for all positive delta. How might we go about proving that? What's a proof idea? So I would like a proof idea that doesn't work first, and then we can see, that perhaps lead us to seeing how to fix it. So often, a good proof strategy is try a stupid idea, and it might lead you somewhere, right? That when you're stuck on a problem, the worst thing you can do is just sit there and be like, oh, I'm stuck, right? No, I don't know what to do, so therefore I'm just going to sit here. Right? You just keep trying things. Just keep trying whatever thing bumps into your head. And as you're trying things, you kind of start to understand things better, right? And then maybe it leads you in good directions. So, if I gave you this problem on an example sheet, what's the first thing you should try to do to see if it works?
What's the number of triangles?
Yeah, count the number of something, right? We should define a random variable, calculate its expected value, right? So idea 1, let x be the number of what? So we want a random variable that encodes the answer to our question. And our question is, does there exist a subgraph of GMP with this number of edges that's triangle free? So the question is, exists or not a subgraph of GMP such that the number of edges of G is m, which is this thing, half plus delta p n choose 2, and there's no triangle in G. And our random variable, whether our random variable is 0 or not, is supposed to encode whether this exists or not. So what should we count?
Number of such graphs.
Those things, right? Yeah, exactly. Exactly that. Right? The number of these things. G in GMP, no triangle, number edge of G is m. Right? Where m is this guy? And what we care about is if x is 0 or not. So what's the expected value of x? Yeah, right. This is the random event. So we're summing over these things. So it's the sum over no triangle in G, E of G is m. I guess G should be contained in Kn, with the probability that G is contained in GMP. Now, how large is this thing? How many triangle-free subgraphs, how triangle-free graphs are there with m edges? Well, our m is bigger than n to the 3 over 2, so Wuchak tells us that this is the answer. But actually here I just want to say this is the lower bound. Okay, so this is really the truth, But let's observe this as a lower bound. This is at least n squared over 4 choose m. And the choice is, and then this is what? This is just p to the m. Right, each edge of G has to be in GMP. That's probably p to the m. What's this thing? This thing is roughly en squared over 4m to the m times p. Right. And what's m? M is this guy, half plus delta pn choose 2. So this is e over half plus delta times 4, 2 plus 4 delta, times, what happened to the pn squared? The pn squared cancel. Sorry, I don't mean that, because there's a 2 here as well, sorry. So it's really over 4. So 1 plus 2 delta. Is that right? That's the wrong way around. Sorry. 4 plus 8 delta to the m. But delta's small, so don't worry about it. So it's basically e over 4. Have I got this wrong? I'm sure I have got it wrong. Thank you. But why? M is like pn squared over 4. Sorry, pn squared over 4. This is e. Sorry. Is that right?
There's still a half plus delta.
The half plus delta and the n squared over 2. So m is roughly pn squared over 4. So it cancels with a pn squared over 4. So it's like e to the m. Right? This was true, sorry, this is true whenever m is much smaller than n squared. So the point about this is it's much bigger than 1. So what's the point? The point is we failed. Right? The method didn't work. Expected number is big when we want it to be small. Or we wanted there not to be any of these things. And the reason, what was the reason? The reason was there were way too many triangle-free graphs with m edges. Because you could take a bipartite graph, a complete bipartite graph, and take any subgraph. So the bad thing is, so what we're worried about are triangle-free subgraphs that are bipartite. In fact, they're all the ones that are contained in this bipartition. Why are they not a problem? Why was that a silly thing to have been worrying about? Why is this a silly thing to have broken our proof? So they are triangle free. They're triangle free in a very simple way, right? They're even bipartite. I mean, the point of this lower bound was take a bipartite subgraph. And now we're saying, but maybe a bipartite subgraph is better. Right? This is supposed to be the best bipartite subgraph. If there's a better bipartite subgraph, if there's a bipartite subgraph that's better than this, then we should just think about those. Is there a bipartite subgraph with way more edges than this? Perhaps it's not so easy to see, because there are lots of bipartite graphs, right? There are like 2 to the n possible bipartitions. Maybe one of them has more edges than this. But it turns out for p large, it's very unlikely. So the concentration in this number of edges is much greater than you need to you can apply a union bound over bipartite graphs. So actually the probability of having a half plus delta by Chernoff, which I mentioned but maybe you've all forgotten. So let me mention just Chernoff again. So Chernoff. What does Chernoff say? It says the probability that a binomial random variable, maybe I'll call it capital NP. Right? So you do n coin flips with probability p of being heads, minus p times n is bigger than t is roughly e to the minus t squared over p times n. There's probably a constant here, but let's not worry about it. Okay? So if you want this thing, so for us, so what's the distribution of the number of edges of G and P? Binomial n choose 2p. Right? And similarly, in any bipartite subgraph, you look at the number of edges here. Number of edges here is binomial n squared over 4p. Right? And this is saying it's very tightly concentrated. So the probability of being n squared over 4, sorry, what am I saying? Of being sort of 1 plus delta times as big as you're supposed to is like e to the minus delta squared times pn squared over pn. Shall I write it out? Maybe I should write it out. Okay, that's right. Right. So the probability that E of, what am I saying? Binomial n squared over 4p is bigger than m, where m is that guy over there, is at most like e to the minus delta squared times pn squared. That's what Chernoff gives you. Right, because your deviation, your t is like delta times pn squared. Little n squared. Right? So that leads to something like this. And this is much, much smaller than 2 to the minus n. Did it make sense or not? So for each complete bipartite graph, how many edges you like to pick up? Well, roughly the right number. What's the chance that you gain so many more in a particular bipartition that you beat this bound? Super tiny. It's like e to the minus pn squared. And p is bigger than 1 over root n. So this is like e to the minus n to the 3 over 2. Right? Much, much smaller than 2 to the minus n. So union bound over bipartite graphs, all of them are good. So bipartite graphs are not the problem. But they were the problem in our proof. So here's the idea 2. All of these bad graphs that are inside this complete bipartite one, all the guys we counted here, we shouldn't count them separately and sum up over these probabilities. That's a stupid thing to do. We should put them all in one container and deal with them one at a time, like in one go, by this argument. I mean, we just dealt with them here. Right? That was us dealing with them. It was easy. So we should put them in a container and apply Chernoff to deal with that container. OK, but what about all the ones that are not bipartite? Maybe we can find containers for them as well. Maybe we can group them in bunches and then just apply Chernoff to each one. If our number of containers is small enough that this bound beats it, then we can apply a union bound over containers. Okay, so that's the idea. So let me state, and I have to say this, or so verb gruppiar, is that right? Agrupar, thank you. I knew I was missing a letter. Agrupar. Okay. So, here is a container theorem for triangle-free graphs. So there exists a collection of graphs on n vertices with the following properties. G is small. Every G in G has few triangles, and for every triangle-free H, there exists a G in G such that H is contained in G. Now, before I tell you what small and few mean, let's just try to put this statement in our heads, because I know it's a bit confusing. By thinking about, so let's play a game. Let's try and satisfy two of these properties, but not the third for each pair. So how do you satisfy the first two properties? Right, so I want you to get a G that's as small as possible, such it satisfies this.
You can have one.
You can have one, even better. You can have none, right? Right? You can satisfy the first two with the empty collection. OK, that was good. What about the first and the third one? It would be small, such that you contain all triangle-free graphs.
All triangles are free graphs.
That's pretty big. It's not that small. That's the complete graph. You can have size 1, right? Just take the complete graph. Right, and finally, if you don't care about being small, but you want these two, so each one has few triangles, and you cover all triangle-free graphs. Just take all triangle-free graphs, right? That's fine. OK, so it's not difficult to satisfy two of them, but once you have three of them, then you're in good shape. So what does small and few mean? Well, there's a trade-off, right? The fewer you want, the more you need. So a natural definition of few, which perhaps for you is also now natural, now you've seen some supersaturation, is little o(n) cubed. Right? If you have little o(n) cubed triangles, you can do things like apply the triangle removal lemma. This is the kind of thing that supersaturation gives you in regularity. Right? This is the kind of thing we've been playing with. Right? It says you don't have any triangles in your reduced graph, for example. And if you do that, then small means less than basically n squared choose n to the 3 over 2. Maybe I should put a large constant here. So this n to the 3 over 2, this looks kind of slightly confusing. And I maybe even written it in a slightly confusing way, right, as a choose rather than, you'll see there's a reason for that. But the point is this 3 over 2. That's the important number. This 3 over 2 is the same as the n to the 3 over 2 in the threshold for m earlier. It's the same as this 1 over root n. Right? The point is that 2 minus 3 over 2 is a half, whatever. The other way around. 3 over 2 plus a half is 2, whatever. Anyway. So you'll see, this is the number of edges in, this is like Pn squared. That's what I mean. It's like Pn squared. Okay. This is like basically more or less best possible. Okay. So let's see quickly why this theorem basically implies that theorem. And then we can talk about how to prove things like this. So who can prove this theorem using that theorem? And Chernoff. We're going to keep Chernoff. I'll keep that line as well. So, what we're worried about is there might exist a triangle-free subgraph of GMP with m edges. Right, that's it. Right? So suppose that there exists H, a subgraph of GMP, triangle-free, m edges. What do you want to do with this H? What can you possibly do with it using this theorem? Yeah, H is triangle free, so it's contained in one of the containers. Right? H is triangle free. That means there exists G in G such that H is contained in G. So let's bound the probability of this. And let's just bound it in the simplest possible way, just using the union bound. Okay? The probability there exists G in G. So what do we want? So we don't want a sum of H. But what do we know? We know that H has m edges, and H is contained in GMP. So this implies that the number of edges of G intersect GNP is at least m. Right? That's what we know. Okay. So we're worried about there exists G and G such that the number of edges of G intersect GMP is at least m. I should rewrite Chernoff somewhere else, shouldn't I? Maybe I'm just going to leave it here. I'm going to just leave this here. This is the application of Chernoff that we care about. I can write it again if we need it. Right. So what is this? Exists G and G such that something is at most the sum over G and G of the probability of this thing. right? Happy so far? So we need to bound this probability. What is the distribution of this number of edges? Binomial, right? It's binomial E of G P. So what we want is for this to be unlikely. So what we want is for M to be bigger than P times E of G. So is it true that M is bigger than P times E of G? And how much bigger? What do you know about G? He's got a few triangles. So what does that tell you? The number of triangles in G is little o n cubed. Tells you what? We would like to know the number of edges in G is not too big. That implies the number of edges of G is at most what? This is the thing you're supposed to know. This is the thing I'm supposed to have taught you. You're just guaranteed it's on the exam. Sorry? No. There are triangle-free graphs with more, right? If I said 0 here, then what would you say? N squared over 4. Right. But I didn't. I said little o n cubed, so you have to add little o n squared. Right? This is the supersaturation that we've proved in more than one way, right? We gave elementary proof of it at the beginning. We can do it by regularity now very easily. Right? It's OK. This is I mean, if I'd written plus t, then here I would have had to put n squared, right? So, t times n, sorry. OK, so we know E of G is at most this. So, but what's M? M is a half plus delta P n choose 2. So M is basically Pn squared over 4 plus delta Pn squared, essentially. And I claim this is bigger than P times E of G, which is Pn squared over 4 plus little o Pn squared. Right? So this delta is exactly what pushes M above its expected value in one of these containers. Right? Yeah.
Aren't the equalities switched there? Because you have E of G smaller than something, right?
Right. So like that. Yeah. OK? More to the point, so it's not just bigger, it's bigger by about delta Pn squared. Right? So up here, we have exactly this inequality. Right? You put the extra, the sort of minus Pn squared over 4 is at least delta Pn squared is like this thing. That's what Chernoff gives us. So Chernoff says that this probability This is Chernoff. Chernoff is like an ancient concentration quality from the 50s or something. So don't think I'm not hitting you with some crazy high-powered thing here. This is just like the standard tail bound. Is what? So you get the same bound for everything. It's size of G times e to the minus, say, delta squared Pn squared. Not being too careful with the constant here. But how large is G? That large. Right? So this thing is basically n to the c n to the 3 over 2 times e to the minus delta squared Pn squared, which tends to 0 if some condition on P. So in this case, if P is bigger than about log n over root n. So I didn't quite prove what I claimed. Right? We have this extra log n. It turns out that in order to get rid of this log n, you need a more technical version of this statement, which I don't want to tell you. So it's not very difficult to get rid of this log n once you have the correct version, but it's a bit hard to understand, so let's not worry about it. Maybe I'll try to mention it a bit later. Okay, so using this result, just the existence of this collection of graphs, this collection of containers, you can basically prove this theorem.
Sorry,
Yeah.
what you're saying is, so the conclusion of this is that there's not going to be to exist K3 free H?
Yeah, exactly. This first step is not likely. Yeah, the existence of the thing is not likely, and therefore the theorem is true with high probability.
Magical.
Yeah, it's magical. Yeah, no, I mean the magic is there exists this collection of graphs. It allows you to just do a union bound over this collection rather than over the whole world. Yeah, and each one of these, because they have few triangles, by this supersaturation result, they don't have too many edges. That's the point. So each of them should be OK, because it doesn't really, in the worst case, it basically looks like a complete bipartite graph. And we know complete bipartite graphs are OK, because there's only 2 to the n of them. OK, now it's worse. We don't have just 2 to the n of them. We have 2 to the n to the 3 over 2 of them. We've got many more. But now we've dealt with all of them, not just bipartite ones. Right? So you take this very simple idea that we had of grouping the bipartite graphs according to the bipartition. If you can prove this more general statement, then the same thing works. So that was motivation for why this statement is interesting. Now let's talk about how you can prove this kind of thing. Right? And perhaps I should say, for all the other problems that I mentioned, and many more, so it's not just about triangles, you can avoid any h, arbitrary long arithmetic progressions, lots and lots of other things. Like anything that you can encode as a sort of forbidden substructure, corresponding theorems exist. Right? Let's just talk about triangles to keep things simple. Okay. So how would you go about proving something like this? I'll do it here. So it's highly non-obvious. I don't expect you to have an idea. So the first, perhaps, idea is to work in a more general setting. So instead of just thinking about triangle-free graphs, let's think about hypergraphs. So let's encode it. The first step is let's rephrase this as a result about hypergraphs. So the hypergraph we're going to be interested in for this recoding is as follows. So I'll call this the hypergraph that encodes triangles. So the vertex set of H, maybe I'll put it over here. The vertex set of H will be the edge set of the complete graph. Okay? The vertices are edges. And the edges of H is going to be 3 uniform. They're going to be triples E, F, G, such that they form a triangle. E, F, G. They're going to be triples of edges that form a triangle. Does that make sense? So it's a slightly weird object. And now, so what do we want? We can have a collection of, what's a graph in this world? There exists a collection of, what's a graph with n vertices in this hypergraph? No, forgetting triangles, just what's a graph? What does a graph look like? Take any graph, map it into this world H. What is it? The edges of a triangle. I mean, yeah, the edges of Kn. E, F, and G are edges of the complete graph that form triangles. Yeah, so how many vertices does H have? Maybe I'll use this notation. Number of vertices of H, and choose 2. How many edges does H have? Right, n choose 3. Right. Okay, so what's a graph? A graph is a set of edges. A set of edges of the complete graph is a set of vertices of H. So it's just a collection of subsets of vertices of H such that, okay, size of G is the same thing. N squared, choose C, and 3/2. Every G in G has few triangles. So every G in G has few edges, right? Of H. And finally, perhaps most importantly, every triangle free H is contained in some G. Maybe I'll just call it something slightly different. I'm going to call it C instead. And then I'll call these C and C to make clear they're sets. What's a triangle free graph here? Yeah, set with no edges, an independent set. So for every I, an independent set in H, these are the independent sets, there exists C in C such that I is contained in C. Right? We just rephrased this theorem in the language of this hypergraph. We've gained nothing, right? Completely pointless. Why do we even bother? So what could possibly be the use of stating something in a more general setting? Yeah, why would generalizing it be good? I mean, okay, so generalization for the sake of generalization is sometimes fun, but yeah, so what tool in particular makes is good for for proving more general statements. Which proof method works better with more general statements than with more specific ones? Induction, right? It's good for induction. So we're going to do some kind of induction.
Sorry.
Yeah.
I just don't understand the subsets of V of H, because there we have fixed number of vertices, right?
Right.
So
Here we also have a fixed number of vertices of the graph,
but
which is like a universe that lives behind. So there's a universe of n vertices which kind of disappears here, but it's still there because you have these n choose 2 vertices of your hypergraph. Right? So these graphs, you should think of them as being collections of edges. These are subsets of the edge set of Kn.
yeah, okay, but the subsets shouldn't have fixed size then? The subsets.
No, the graph can have any number of edges. Right. Yeah, so I know that this hypergraph is a bit confusing when you're first trying to think about it. So it's normal that, right, you've got two different things called vertices and two different things called edges, and they're not the same thing. In fact, one of them is the same as the other one. Yeah, it's not very good. The naming is not very good, but we're kind of stuck with it. Right? Now, the vertices here are edges here, and a graph is a set of edges. And you shouldn't think of the vertices. You should think of a graph as being a set of edges. Right. Okay. So it's not so obvious how to prove something like this. So let me draw a picture, and then maybe I'll try and talk about proving a version of this for two uniform hypergraphs of the graphs. So here is our H. H is now, you should think of as being so it's some hypergraph, and maybe the edges are size 3. Okay, so this is just some 3 uniform hypergraph. And what do I want? I want for every independent set in H, I want to find a container for it. But I want there to be few containers. So there might be lots of independent sets, right? There might be way more than this many independent sets. Like with triangle-free graphs, that's how many there are way more of them. So I need to find them, but I need to find the same one for lots of them. So what do I do? So here's an independent set. Maybe it's pretty big. Here's I. How do I find its container? So what we're going to try to do is find a small subset S of I that we're going to call the fingerprint of I. How do you say fingerprint in Portuguese? Digital. Okay. So this fingerprint is going to encode the important information about I. In particular, what it's going to tell us is that there's some set over here, x of s, which is disjoint from I. And x is going to be large. Delta times number of vertices of H. So we're going to find this very small fingerprint such that there's a set x depending on s, not depending on I. Right? Only depending on s, which is disjoint from I and is large. What we're then going to do is iterate this lots of times, throwing out delta proportion of the vertices each time until we get down to a set with few edges. And then we stop. So 2 claims. So we're going to find why is I contained in C, because the thing we throw away each time is disjoint from I. Okay, so C is just going to be what's left after we've thrown away all this stuff. Why did it have few edges? Because we just continued throwing away until it did. And why is it small? Well, the size of S is going to be at most, so some tau times number of vertices of H, where tau depends on H, and in this case it will be 1 over root n. So S will be small enough that the number of choices for S is at most, well, n number of vertices of H choose this guy. So the number of choices of X is that. And then we do this a bunch of times. We do it a bounded number of times, throwing away a quantum portion each time. After a bounded number of steps, we've still only had basically this many choices. Right? So this is the number of choices for the fingerprint, or the sequence of fingerprints as you throw things away. So that's the idea of how to prove it. We need to try and find this fingerprint somehow. Okay, so how to go about finding this fingerprint? Yep.
Somehow X is bounded. The size of X is bounded by the size of S. Something I didn't get why X is bounded.
X is big. S is small, but X is big. Yeah. Yeah, so that's the difference. We have to keep S small, but make X big. So let's see how we do it if, instead of working in a 3-uniform hypergraph, let's try and do this exact strategy in a 2-uniform hypergraph, a graph. Okay. So let's try and state a container lemma, which would be one step of this iteration. Right? So we're iterating this process. What I've drawn is one step. You take your eye, you find a fingerprint that gives you this X, which is big. And what we're going to do is then remove that and iterate. Just keep repeating until we have few edges. But this lemma is just going to say, let's do one step of this. So how do you do one step? So let's suppose we have a graph G, which has got our H, which has average degree D. So for all independent sets in G, there exists an S contained in I and an X of S disjoint from I, depending only on S, such that size of S is at most V of H over V of G, sorry now, over D. Maybe I'm cheating very slightly here, so maybe I want to add in a small constant. let's see what we get in the proof. And size of x is at least delta times v of g. V of g. That's n vertices. Do anything else?
Should it be x of s?
Thank you. Yeah.
The sin s takes the regressive function of whatever subset.
Right, so yeah, so a slightly more complicated formulation of this would be there exists functions mapping independent sets to fingerprints and fingerprints to containers. Yeah, so there's some deterministic function that takes small sets to, so small sets S to large sets X. And this, and right, so the, yeah.
Doesn't x depend on I?
X only depends on S.
But
It depends on,
I.
right, so it depends on I, but only through S. So in particular, two I's, I and I prime, with the same S, will have the same X. Right? So it depends on I, but if I and I prime both have the same fingerprint, then they must have the same container. Okay? That's the point. Yeah.
Strategy would be taking the union over all independent set that contains S and trying to find something outside of it.
So that might be a strategy. So we have to construct S, right? So we want to construct S in such a way that this holds. We want to construct S and X of S at the same time so that this holds. So it's a bit subtle. So maybe I'll come over here to do this. Right. So here's the idea. This statement, there's a chance I'll modify it in a bit when we prove it. But let's just see what this is the idea. So here's what we're going to do. It's a very simple strategy. We're going to order the vertices basically so the high degree vertex on the left and the low degree vertex on the right. But not quite by degree. So this will be the vertex of max degree, or a vertex of max degree. But this will be a vertex of max degree after removing this vertex. Right? This is a vertex of max degree after removing these two, and so on. So each vertex is a vertex of maximum degree in the graph to the right. And what that has the important property that, therefore, the degree of this vertex to the right is at least the average degree in what's left. Okay, that's what we really need. Okay, so this is the max degree order. Now let's go along vertex by vertex, asking the vertices questions. And the question is, first vertex, are you in I? Right? That's basically the only question we can ask. So what are we given? We're given an independent set I, this independent set. We want to find this fingerprint. So let's go and ask vertices if they're in I or not. If they are in I, let's put them in the fingerprint. If they're not, then we can put them in X. Right? So, first vertex, are you in I? This is the in I question. He says no. So I say, great, thank you very much. I'll find some red. And some green, maybe. Maybe yellow and green. Works well. So I'm going to put you in X. Second guy also says no, so he also goes in X. But the third guy says yes. Yes, I'm in. So we put him in S. But what else can we do now? We found someone who's in I.
Put the neighbors next.
Exactly. This guy might have some neighbors over here. In fact, he probably has lots of them because he's a pretty high degree vertex. Right? These guys are now immediately, because he's in your independent set, they cannot be in your independent set. So they can also go into X. Now, there's probably like D of them or so. And then continue. Next guy, are you in? So actually at this point what we should do is reorder the vertices so we're picking the max degree vertex of what's left. Right? And then continue. So this is one step. So what happens in one step? Well, we're here. So yep.
Could you explain again why you can, once you find a vertex in S, you can...
Because this guy is in I. He said yes to being in I, and I is an independent set. So if you find a vertex in an independent set, you know his neighbors are not in the independent set, because if one of them was, you'd have an edge. Yeah. So what happened? We added one vertex to S, so the size of S went to S plus 1. And what happened to the size of X of S? So first, why does X only depend on S? Why do the set of vertices we threw into X only depend on S?
This is not clear to me because you're asking if they are in I.
You're asking if they're in I, and what's happening, if you're saying if they're getting some no's, okay, they're also not in S. But as soon as you get a yes, you put that vertex in S. So every piece of information you have about I is encoded in S because you put that vertex in S. In particular, two sets I. So the point is, this ordering, the ordering in which we asked the questions, did not depend on I. Right? It was just a property of the graph. So you ask the same questions for these two sets, I and I prime, until you arrive at a vertex where they say yes. And then either if that vertex is in one and not the other, then they have different fingerprints. Because you'll never ask that question again to that guy. Perhaps I should say that, because he goes in X. He gets thrown away in one of them. Right? So if the same vertex gets put into S for both of them, that means you threw away the same vertices here as well. And so the next step of the algorithm is the same as well. You're always asking the same question. So nothing changes in the algorithm until there's a difference that's encoded in S. Until there's a vertex that's put in S for one of the sets and not for the other one. And so if you see a difference in X, you also see the difference in S. So, yeah?
The first step is until we have the first yes?
Sorry?
The first step is
Yeah.
until we have the first yes? Or because
Yeah, you just run it until you get a yes, exactly. Yeah. And then you sort of reorder the what you have over here and repeat. You just add 1 to S each time.
So why isn't, maybe this is silly, but why isn't S equals to I?
Because you're going to stop. Yeah, we're not going to carry on forever. Yeah, exactly. Yeah. Yeah, so the question is, when do we stop? And we stop when S gets to the correct size, and we claim, so the correct size is going to be n over d, and we claim that x of s is already big. Or if you like, we stop when x of s is big, and we claim that s isn't too big yet. Right, so we haven't taken too much. And what we have to do to show that, we just need to show that in each step we throw a lot of things into x of s. So how many things do we throw into x of s? Well, Right, so it's the number of things to the left and the number of things to the right. So I claim that one of those is at least d over 2, maybe? Or I should put 4 or something. Anyway, I'll put 2 for now. See if it works. So why is that true? Well, when you come to this vertex, so I remember the condition I've missed, so we'll see it now. We come to this vertex. If his degree forward is at least d over 2, then we're fine. So let's suppose it's not. So this vertex, his degree forward is less than d over 2. This vertex had at least the average degree in this set. So that means the average degree over here is at most d over 2. The average degree at the start was d. So we've thrown away at least half of the vertices. Sorry, at least half of the edges. What I like is that means that we've thrown away lots of vertices also. So I want to say that x is already big. So what do I need for that? I need something I didn't tell you. I need a max degree condition. So let me add it. So for all C, there exists a delta such that. For all I and I, there exists S in I and x of S intersect I is empty such that size of S is at most n over d, size of x of S is at least delta times n. So if we've thrown away more than half the edges, and every vertex has degree at most a constant times the average, then we must have already thrown out at least a constant proportion of the vertices. So I write that. What do I call this guy? This guy is U. Degree, what do I want to call? Maybe I'll call all of this entire world, everything that's left, I'll call it A. And I want to say the number of edges of G inside A is at most the number of edges of G divided by 2. Right? Because the average degree has gone down by at least a factor of 2. So the number of edges must have gone down by at least a factor of 2.
Sorry, just one thing.
Yeah.
Your order is the bigger degree to the lower degree?
So greedily, so each vertex is a maximum degree vertex in what's left. So A should include this guy, I guess. So if the degree of U is at most d over 2, then the average degree in A must be at most d over 2, which means that you've lost half the edges. So I'm saying something totally trivial, so this should be OK. This is just a step. You look confused. What's the confusion over here? Wait. Yeah, please.
Your thing is you're throwing vertices out in the middle of the process.
Yeah.
And that's why I don't find it obvious that you'll get happy edges.
Ah, right, because it's even fewer because A is smaller. So this is at most, so the average degree is at most d over 2 times A, over 2. And this thing, E of g, is equal to d times n over 2. Right, so A is smaller than n, so it's actually even better than this. Yeah, so the throwing out helps you, doesn't hurt you. But it's a good thing to check. Right? So there's the average degree is half as big, and there are fewer vertices. So it's even fewer. So you've really thrown away at least half of them. OK, but the max degree is only constant times d. So that implies that the size of A must be at most what? Well, n minus. So you get to throw away, each vertex throws away at most c times d. So it's at most E of g over 2 divided by c times d. Right? You lost this many edges. And each vertex removed only this many, at most, by the max degree condition. So that means it's at most n minus E of g over d is something like n, right? What is it? E of g equals dn over 2. Right? So dn over 2 cancels with the d, n over 4c, which is less than 1 minus delta times n. Actually, 1 minus 2 delta times n, maybe just to be safe, if we pick delta small enough compared with c. Right? For every c, there exists a delta. So delta is like 1 over 8c. Something. OK? So we've thrown away at least 2 delta n vertices. If delta n of them were thrown into x, then we're already happy. We would already have stopped. So delta n of them must have been thrown into S. But, so here comes another condition. If d is large, then that hasn't happened because otherwise the previous condition already broke. And why didn't the previous condition already break? Because, OK, let's run the process until this breaks. While this is happening, you're removing d over 2. So x of s is going up by d over 2 at each step, every time s goes up by 1. So if s had already gone up to n over d, x of s would already be at least n over 2. But if x of s is already n over 2, we've already stopped. So while this is going, while these two things, so while s is small and x of s is small, this is true. Right? If this fails, it means already one of these have failed. So they continue, and the one that breaks first is this one, because you can't do n over d steps like this without x of s getting to be n over 2, which is too big. So this very, very simple argument, this very, very simple algorithm, proves this lemma. Right. So there's not really very much time left. So I'll just say a few words vaguely about how this generalized to hypergraphs, and then maybe we stop. So right, so for graphs it's very simple. So this was sort of what Kleitman and Winston did, and then it was generalized by Sapozhenko, who used it to prove a bunch of stuff in the 90s. So this already is quite a powerful lemma. Even though it's pretty simple to prove, you can do a lot of really interesting stuff with it. But right, for hypergraphs, you want to prove a sort of a corresponding statement. So the problem is, you try to do the same thing. So we order the vertices of our 3 uniform hypergraph with its max degree order, and then go along asking questions Are you in I? No. Are you in I? No. Are you in I? Yes. Okay, so everything to the left we can put into X. This guy goes in S. But now these things, what are these things? These are neighbors of this vertex. But it's a 3-uniform hypergraph. So these aren't vertices anymore, they're pairs. So instead of having these yellow vertices we put into X, we have a bunch of forbidden pairs. Okay, so let's just record them where they are and continue. So we continue. Instead of throwing them away immediately, just keep going. Pick lots and lots of elements of S until we have enough edges that we decide, all right, now we've got a graph, this graph of forbidden pairs. Once we have enough edges, we can run this algorithm on that graph. Right? Now, you have to be careful because we want a max degree condition. So we have to make sure, as we're building up this graph, we maintain this max degree condition. So we decide what max degree we're happy with, and we just say, let's not add anything above that. Okay, we just don't allow ourselves to add edges that make the max degree bigger. Okay, but then we still have to show that we're going to end up with enough edges. And to do that, we need, on our hypergraph, not only a max degree condition, but a max pair degree condition. So you don't want any pair of vertices to be in too many triples. In general, if you're doing a k-uniform hypergraph, you don't want any L set to be in too many edges. If you have all these conditions, and you set them up correctly, you can run this induction, and it all works. And it's only about like 5 or 6 pages. It's not very complicated, right? You do keep track of things. It's all right. Okay. What it gives you is a lemma that looks like this, that you can iterate, and you can prove a container theorem of this type for an essentially arbitrary hypergraph, as long as you have control over its degrees, its degrees of the pairs, and so on. And all of the examples I gave you, so the hypergraph encoding graphs, the hypergraph encoding arithmetic progressions, lots of other similar things, you do have control over these degrees. And when you're running the iteration, as long as you have many edges left, the argument still works. It breaks down when you're left with few edges. And then you stop anyway, because you're happy. Okay? You stop, and you apply supersaturation. And you find out what your thing looks like. OK, so I don't know. If you're interested in learning more about this, I have some notes on my website and a survey that some of us wrote. And so there's some stuff you can find. Right, yeah, let's stop a bit early today. Wednesday, you have the exam. Hopefully it won't be too difficult. Do you want a difficult exam or a not difficult exam? OK, so I'll put on, I guess it'll be a bit more than half from the first part of the course, and I'll stick on, like, there'll be a regularity question, there'll be a dependent random choice question, right? Maybe one other thing from the second half of the course. Yeah, and then maybe like four not too difficult things from the beginning. Yeah, so go over the first exam again, make sure you can do those problems. I might put the same thing on. Go over the listas, particularly the first lista. Yeah. The second one was harder, I know. So the easier things from the second lista. Yeah. OK, questions? OK, see you on Wednesday.